Case Western Reserve University's Institute for the Science of Origins proudly presents the Origins Science Scholars Program. The Institute advances the scientific understanding and application of the origins and evolution of human and natural systems. The Origins Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision. It is my distinct pleasure to introduce tonight's speaker, Nathaniel Starkman. Nathaniel is a PhD candidate in astrophysics at the David A. Dunlap Department of Astronomy and Astrophysics at the University of Toronto, where he's a fellow of Massey College. He received his BS degree in physics and in astronomy from Case Western Reserve University in 2018. Nathaniel grew up in Cleveland Heights, Ohio, and we would have liked to have him back in person to give this talk, but are delighted to have him here by Zoom. As you might have guessed, I'm Nathaniel's father, so I am particularly delighted to welcome him to speak about dark matter in the Milky Way. Nathaniel.
Thank you for the introduction. Today I'll be speaking about dark matter and the Milky Way, the case of the missing mass. This is an ongoing and active investigation. And as we'll see, while there's plenty of evidence, no suspect has yet been apprehended. Hello, I'm Nathaniel Starkman. I was an undergraduate here at Case Western Reserve University in 2018, but I'm now a PhD candidate at the University of Toronto, working with professors Joe Bovey and Jeremy Webb, researching dark matter in the Milky Way. Today, we'll be looking at this open case, this mystery of the missing matter, told in three parts. In part one, we will find the scene, in this case, our Milky Way galaxy. This is going to be a years-long journey culminating in the year 1923. In part two, having identified the scene, we can start looking for evidence of the missing mass all around us in the Milky Way. And in part three, we'll expand our scope somewhat and look for evidence in the outskirts of the Milky Way and even a little bit beyond. So part one, arriving at the scene. Right, in the beginning of any Sherlock Holmes or detective story, we have the discovery of a crime or a crime scene. Are you ready for it? Here it is, the night sky. If you're out in nature, all you have to do is look up. And if you have the privilege of being in a really dark place, distant from any city, this is what you might see. Right, we have thousands of stars in the sky. And as you can see in the center here, you have this band. It kind of looks like spilt milk across the sky, right? This is the Milky Way. We'd be tempted to say, look, we've just found the scene when it can drop in a detective and start gathering evidence. Maybe the dark matter is over here, or maybe it's just over there, right? Even though this scene is just above us, all we really have to do is look up, realizing that we have all this missing matter, that we have this mystery case is not so simple. It's going to be a long journey through human history to what we're looking at is such a mystery, and that what we see isn't all that there is. So to open this case, we need to understand this history and make a really profound discovery that we live in a galaxy. The band of the Milky Way through the center there is only one galaxy among many, and almost every star we see in the sky is part of the Milky Way. When we finally make this discovery that we live in a galaxy, finally we'll realize that the game is afoot. So that was a snapshot of the sky. If you look up at the sky and wait for a long time, this is what you'll see, right? The Earth is clearly stationary, and the heavens rotate about the poles, right? The sun, the moon, the planets, they all do some strange stuff. But we actually have a really good explanation for this. It's the firmament, right? You may be familiar with this from the Bible or many other religious texts, right? The stars that we see in the sky, they move together because they actually are right next to each other in a single layer. The sun, the moon, and all these planets, well, the reason why they can do their own thing, move in their own way, is because they have their own distinct layers. And that each one moves separately. By the 3rd century BCE, we know that the Earth is a sphere. So logically, we evolved this model to the Ptolemaic model of that of the celestial spheres. these perfectly ordered spheres in which everything lives. The stars we put in what's called the primum mobile, right, this outermost sphere at the edges of the universe. The planets, the moon, the sun, our solar system is the entirety of the universe besides that. And each of these have their own perfect crystalline sphere, right? It's the Platonic ideal. This is actually a model that we can make predictive science with. We can say, tomorrow, Mercury is going to be over here and Venus over there. And when we do that, it doesn't work so well. So people get clever and they say, maybe it's not just these perfect crystalline spheres. Well, it is for the stars, but within that, the planets, the sun, the moon, they all move in circles within circles within circles, right? The Ptolemaic model, it's called epicycles. And it adds all these details, and we actually get really, really good at predicting the locations of everything. Of course, this is wrong. We're not at the center. But the situation isn't going to improve until we get to heliocentrism, right? And I want to stress that what we're looking at is really just a model of the solar system. Our conception of the universe is bound in this primum mobile, this single layer of stars out here. We don't have a concept really of the Milky Way, not as a separate object. It's just something like painted on this sphere, or of any other galaxy beyond that. All that science up to this point really has is a model of the solar system. And in order to talk about dark matter, we need to move beyond this. So for heliocentrism, we have the Copernican model in the early 1500s, but even Copernicus had the primum mobile to hold the stars, right? And heliocentrism wasn't an excellent model until Kepler came along and told us that not everything lives in perfect spheres, it really lives in ellipses. But he too didn't realize that beyond the solar system isn't just a perfect crystalline sphere. Really, the first hint that the universe extends beyond our small solar system is in 1584, proposed by Giordano Bruno. Right. He scraps the primum mobile and proposes an infinite universe populated by stars. Giordano Bruno is a visionary, and he imagined, very little funnily, very much without evidence, that all the stars are like our own sun, many of them with planets and comets orbiting around them. And it's a spectacular idea borne out later by centuries of observation. And I want to emphasize this moment in our journey to the Milky Way, right? It's a turning point in history. This is the first time we really have an idea that the solar system isn't all there is, that beyond it are an infinite space full of stars, right? This is the first time since the literally biblically old and probably almost older idea of the firmament that we've finally expanded the solar system. Okay, so great. Now we have a solar system, and beyond that, an infinite universe of stars. We return to the night sky. We see the band of the Milky Way going up and across. But what's this, right? This isn't just stars, right? This isn't part of the Milky Way. What we're looking at is the Large Magellanic Cloud in the upper right, and in the lower left is the Small Magellanic Cloud. The Large Magellanic Cloud now we know to be a satellite galaxy of our own Milky Way, right? And around 1/10 as big. This doesn't actually fit with Bruno's model. He had this idea of the infinite universe populated by stars, but we have these tight collections of stars beyond our own Milky Way, right? Is the Large Magellanic Cloud part of the Milky Way or not? People at that time had no way of answering this and debated it quite rigorously. What about other things that we see? The Small Magellanic Cloud, Andromeda, other groups of stars, right? These were very puzzling and just sort of fell under this catch-all term nebulae for things that people thought were inside the Milky Way and were their own collections of stars, but didn't really fit in this beautiful universe of Giordano Bruno. So again, what we're at now is only the Milky Way. We moved from the solar system out, but we haven't yet been able to prove that there's anything beyond the Milky Way. So the whole universe is the Milky Way, and we can't really talk about dark matter in the Milky Way without talking about dark matter in the whole universe until we realize that we're just one galaxy among many. So that brings us to the great debate of 1920, all the way from Giordano Bruno 1580 to 1920. We have this debate at the National Academy of Science in Washington, D.C. On the one hand, we have Harlow Shapley, who says, these things that we see, Andromeda, the Large Magellanic Cloud, they are nebulae and they are inside of our galaxy. There is nothing beyond. On the other hand, we have Heber Curtis, who said, no, these are galaxies in their own rights. Our Milky Way galaxy is not the only thing there is. Andromeda is far outside the Milky Way. We have an infinite universe full of galaxies. And both were brilliant scientists, but only one could be right. Rather than having to wait another almost 500 years, in a mere 3 years later, Edwin Hubble in 1923 makes a really important, but actually a little bit mistaken measurement. He uses these special types of stars called Cepheid variables, although he mistook the type that he was looking at, to measure the distance to Andromeda, right? This is one of these nebulae inside of our Milky Way, or so we think. In fact, he finds that the Andromeda Nebulae isn't a nebulae at all. It's a galaxy. It's 285 kiloparsecs away. That sounds like a big number. It is a big number. It's much, much bigger than our Milky Way is across. Turns out he was wrong. It's actually 3 times further than that, which thankfully still makes it its own distant galaxy. So this settles the great debate. In fact, the Large Magellanic Cloud, the Small Magellanic Cloud, Andromeda, and all these things we're starting to see, these are not nebulae inside of the Milky Way, but galaxies in our own rights. Finally, we actually have this idea of our galaxy and other galaxies. We are not the galaxy. The Milky Way is just one galaxy among many. In the decades since, we have, of course, found billions of galaxies with things like the Hubble Space Telescope and the Deep Field with these beautiful, beautiful images. So we've gone on this journey from the earliest time that humans have ever looked up at the stars to a realization that what we see, this band in the sky, is not the whole universe. It's not the primum mobile, some perfect sphere at the edge of the solar system. In fact, what we see is the Milky Way, which is just our galaxy. Beyond that are other galaxies. And maybe, as Giordano Bruno imagined, they have their own planets and life on them. But finally, we have this idea that we live in a galaxy. And when we go looking at the depths of our galaxy, we're going to find just how little we understand it, how much mass is missing here and elsewhere. It was certainly contentious, right? They didn't understand a lot of the things that go into these types of measurements, right? It turns out the reason why Harlow Shapley and Heber Curtis and also, were very, very wrong about measuring these things when they tried to do it was they didn't understand things like dust, right? So if you try and measure things one way, you get a really different answer than if you measure it another way. But Hubble's measurement does eventually settle things because it uses something that's relatively incontrovertible. It's not something that's just based off of the brightness. Although the reason why it gets it wrong by a factor of 3 is, in fact, partly the dust. He uses these special stars which pulse and then get brighter and then get dimmer and then brighter and dimmer. And the rate at which they do that tells you exactly how bright they really are. And so then you debate on the difference between what you see and what you expect, and you use that to get the difference. And I don't think Shapley was very pleased to learn that Andromeda was not so close to us.
Did Hubble know that he was wrong in his lifetime?
Yes. Yeah. It was, in large part, very much a mistake by him that he should have realized. He used the wrong, there's many types of Cepheid variable stars, these special stars. And he used the wrong one. He thought he was using one type when in fact he was measuring another. And in his lifetime, people made much better measurements, not only of Andromeda, but of places like the Large Magellanic Cloud and other places. So the exact measurements have continued to improve during his lifetime.
Great. So that was a question from Barbara Fidel. David Moore asks, so do we have it right now? Could it be totally different from what we think it is today?
Well, thankfully, we've moved on to Prima Mobile. I guess nowadays, one might say the Prima Mobile of our time, the sort of surface on which everything happens, is the cosmic microwave background, right? That is the edge that we can see. And we think that it is a nice, that it actually happens pretty much all at the same time. So it's a good question. We think that is the right answer. Until someone clever comes along and shows us we're wrong. I guess that is the Prima Mobile of our time.
Great. Let's see. Lots of questions. So is this the same dust that kind of accumulates on your windowsill and stuff?
It's a good question. Yes, ish, but no, but also no. I mean, we use the word to mean much the same thing, right? It's just, the stuff that just sort of accumulates here and there. In fact, the dust that accumulates on your windowsill, you might not be happy to find out, is largely human skin and hair. But in space, right, the dust that what we see is, most of it comes from old stars that have blown up, right? They process all this matter. They start from pristine gas, so this is hydrogen and helium. They process it into the heavier elements and blow it out in supernovae or planetary nebulas. Some of that gets recycled into stars, and other stuff like we call dust is this enriched gas full of more complex molecules even. There's alcohol in space in case you get thirsty, and other interesting pre-organics. All these things that come out of stars and then planets that never formed and stuff like that. So it's the same stuff in the sense that what is in dust will help form our planets, but different in that it's there's nothing living in it, or it was never alive. All right, part 2, discovering a disk of evidence. Right, we've arrived at the scene. It took us most of human history up to 1923, but here we are. Let's drop in our detective magnifying glass in hand to start collecting some evidence. Right? Broadly speaking, the stars in our galaxy, the Milky Way, and that's what we're looking at now, live in one of 3 places. We have at the center the galactic bulge, and in the very center of that is the supermassive black hole. In this thin disk, that's why it's called the disk, around that we have a disk of stars. And this actually is where the sun lives, around 8 kiloparsecs out, which is around 25,000 light years, give or take. So not too close, not too far. And then surrounding that, we have this diffuse cloud called the stellar halo. And last but not least, we actually have what I study, these little red dots called globular clusters, which are like little mini galaxies. They're these tight collections of stars that are the satellites of the Milky Way and orbit all around. Let's start in our own backyard where we live. We're going to start with the disk. Our galaxy is in motion, right? From the smallest comet up to the largest star. And in the disk, the stars are moving all the time. Their motion is actually complex. They move up and down while they go around. But we're just going to look at this bird's eye view, top down, for now. And when we do, what we see is the stars orbiting around the center of the galaxy, going around. Many of these stars are on a pretty close to circular orbit, kind of like the Earth is on pretty close to circular orbit around the sun. right? And if we were to say, what do we expect when we look at this orange star versus this yellow star, this star that's closer to the center of the galaxy versus farther away? Well, we would say maybe we expect something like the solar system, right? Where close planets go around really quickly, and the farther away you go, the slower the planet moves, right? This thing we call a rotation curve. We'll see that in a second. Turns out we can do exactly what we see in the solar system. Well, we can do it with the Milky Way, right? We can look at this orange star, we can look at this yellow star, and instead of measuring how fast it goes around the sun, we can measure how fast it goes around the Milky Way. For something like the sun, this is around 220 million years, moving pretty fast. And when we do this, remembering that the orange star was closer in and the yellow star was farther out, what we expect to see, what we should see if the Milky Way worked like the solar system, is this dotted line, right? This orange star that's closer in, it should be moving faster around the center of the Milky Way than this star that's farther out, right? But we don't see this. We see something that's really odd, right? The speed, it doesn't decrease with distance. That yellow star that's further out is moving just as fast as that orange one. And this defies all expectations if we count up the matter in the Milky Way. And this is pretty much how we do it for all of these expectations. We go around and we actually count by looking at how much light there is. We add in the gas and the dust and the stars, you add it all up together, and you say, what do I expect? Well, you expect something like the solar system. You expect to see this dotted line. That is how the stars should be moving if they only felt the gravity as we know it from the mass that we can see. Right? So there's this big difference between the speeds we see and the speeds that we expect. There's a wonderful Sherlock Holmes quote, perhaps you're familiar with it. Once you eliminate the impossible, whatever remains, no matter how improbable, must be the truth. So clearly we have something that defies our expectations. Let's ignore that dotted line for now, what we think we should see, and ask us just what is the flat rotation curve really telling us? What is what we actually see telling us about the matter in the Milky Way? And what it's telling us is that the farther out we go in the galaxy, the more mass we see. Now, this is to be expected. If you recall the disk, right, the more you go out, the more disk you have, so you should see more matter. But you don't expect to see a lot more matter, a little bit more matter, but not that much. A flat rotation curve is telling us that instead of increasing just with the little bit that you'd see in the disk, adding in the little bit that you have in the halo, what you're actually seeing is double the radius means double the mass. The rotation curve is telling us that there is so much more mass out there than what we see. And it behaves, it increases with distance in a way that we can't account for, right? So when we put in that expected rotation curve, that difference between what we see and what we expect, right? That space, that is filled with matter, right? That is what is giving us the difference between expectation and reality. This is the Milky Way's dark matter halo, right? We don't know what is the missing mass. That is the great mystery, but now we know it's there, right? It's this difference between the two curves. In total, around 90% of the Milky Way is dark matter, only 10% is normal matter, like we see in the disk. And the flat rotation curve is telling us not only that there's a lot of missing matter, but it also tells us where that matter is, right? If this missing matter were all in the center of the galaxy, in that like supermassive black hole, that wouldn't fix this, right? It would just still look like the expected rotation curve. What we would have is almost like making the sun more massive and saying, why don't the planets all move at the same speed when you go further out, when instead they go like that? It's also telling us that we can't just say, oh man, we didn't measure the mass of all the stars right. Let me take my mass dial and crank it up, and now every star weighs 10 times as much as it should. Right? Again, that doesn't work because where this dark matter is doesn't match where all the stars are. So this difference between what we see in this rotation curve and what we expect not only tells us that there's so much missing mass, this great mystery, it's also telling us that the distribution, the location of all this matter doesn't really match the location of all the normal matter. Okay, so that was us looking top down at the disk, and we saw how everything moves around. I said this isn't how stars move in their entirety. Not only do they move around, but they also move up and down, in and out of the disk while they're going around. This motion that looks sort of like this as it goes around. So we can see that in the side-on view of the disk, right here with the star going in and out of the disk, up and down. Right. Turns out that most stars don't live quite long enough to go that, that full multi journey up, journey down, journey back up. But if you add up, if you look at all of the stars in total, this is what they're all doing. And why are they doing that? Well, it all comes down to gravity. Gravity is kind of like a spring, with the spring on the disk and the other part on the star. The more mass that is in the disk, the stronger the spring. So the less distance that star can get away from the disk for a given speed, coming out of the disk. Weak springs mean that the star, when it's coming out of the disk, it has enough speed to go much, much, much further, and that spring can't, pull it back quite so fast. So again, this is what we see. The stars held, by gravity's spring. But if we were to count all the stars in the disk, all the gas, all that dust in the disk, what we think we should see is a much weaker spring. Right? Again, just like the rotation curve, we have this difference, a large one, between what we expect. We expect here this weak spring, and in the rotation curve, we expected kind of like the solar system, this rotation curve. But what we see is this strong spring here and that flat rotation curve when we look out. So what does this mean in this side-on view of the disk? Well, just like the rotation curve, it means that there's a lot of missing mass. There's something that is making our spring much, much stronger than we think it should be, right? And that mass is spread out throughout the disk. How do we know this? Well, because the spring is really strong here where we are, but also over there where that star is, and even over there, way over there, on the other side where that star is. Everywhere we look in the disk, the spring of gravity is making sure that stars can't escape too far out of the disk. Their journeys are short and sweet, and they spend most of their time bound because of the dark matter inside of the disk. Right, the spring of gravity is much, much stronger than just what we see. Right, we are back at this first picture. We looked at the rotation curve and used that to understand how stars in this Milky Way that we see are going around the galaxy, and how the further away we look, instead of the slower they move all at the same speed, which means that there's so much dark matter. But also, tilting your head and looking at the stars going up and down and up and down, in and out of the disk. We also see that gravity's spring is making sure that our disk is really thin, that all this dark matter means that the disk of stars don't extend into much puffier formation much further out. Right. So what we've seen in this night sky, what we've seen all along is holding so many of these clues towards the missing mass, towards the existence of dark matter. This ends part 2, this local view of the disk. Now it's time for some questions.
We have one from this part, so we'll start there and then go back to some of the older questions. So Chris Wilmoth asks, the bodies at the ends of the springs that you showed, some are moving out while others are moving back in towards the disk?
So really, the spring is just gravity, right? And it's, as we know, the further away you get, actually the weaker gravity is. So with a star, what's happening is, let's say it starts over here inside the disk, and it's moving. It's not just staying still. It's moving with some speed going up, right? It's going to escape the disk, kind of like you jumping on the surface of Earth or throwing a ball. And then, right, it's going to get pulled on by all of the mass inside the disk. Gravity is going to slow its motion up, just like throwing a ball. Then it's going to pull it back down. But unlike what we think of when we think of just throwing a ball, when it hits the surface of the Earth, the ball stops. Here, the disk, though it looks solid, is almost empty. Just like pretty much everything in the universe, almost everything is empty space. So when that star comes and meets the disk again, it doesn't hit anything. It goes right through. And now it's just like that same ball has been thrown, but on the other side of the Earth. Turn everything over. It goes up, gravity slows it down, and it pulls it back in, and that like that. And so the reason I use the spring is like when you have something on the end of a spring, right? It just bounces up and down, up and down, up and down, oscillating until it finally comes to rest. And so that's how like this works. Gravity's spring is really pulling it back to the disk and then through to the other side.
Chris Cullis asks, why did the dark matter assemble in a planar disk? But given that it started, you haven't talked about this, but it started way out there. How did it end up in a planar disk?
It's a great question. So the truth is, it really mostly isn't in a disk. The dark matter is really in this sort of roughly spherical halo all around the Milky Way. And that turns out to be important. We'll see that in just a second. But there is actually more dark matter near the disk than there is elsewhere, and that's just because of gravity, right? The mass that's in the Milky Way of normal matter attracts, right, the stuff that's dark matter by gravity, and they can interact by gravity and so accumulate a little bit. So there is actually more dark matter than you would just expect from us being inside of a big spherical blob of dark matter around the disk, but it's not that much more. What we're really seeing is the addition of just some of this extra dark matter here. So this effect, these vertical oscillations are a little bit more subtle than something like the rotation curve, where we're getting all of this spherical mass of dark matter that surrounds the Milky Way.
And what about the ordinary matter? How did it all end up in this disk, or so much?
Yeah. So there's a word that distinguishes between what dark matter does and what normal matter does, and that's called dissipation. Normal matter can, when it interacts with itself, can shed some of its energy in a variety of ways. And when it does that, instead of just streaming past each other and never really interacting like dark matter, it can shed its energy and then settle down. And it turns out when you do that, even if you start out with a spherical blob, there's just a little bit, kind of like a figure skater, rotating slowly. If there's just a little bit of rotation, as it collapses down, dissipating energy, it spins up and forms a disk.
Robert James asks, is all of empty space filled with dark matter, or what percentage of apparently empty space is dark matter?
This is a wonderful question. So if we're looking in the Milky Way, the answer is it's all full of dark matter, right? There's a lot of dark matter. Although, truth be told, it really actually depends on exactly what dark matter is. If dark matter is really small particles, like these things called neutrinos, then there's a lot more dark matter in every nook and cranny of the Milky Way. If it's these larger things, like maybe something that's a solar mass, well, then just like there's basically nothing between the Earth and the sun, right? That's sort of much more empty space than you'd find on Earth or in the sun, right? Then there's not going to be dark matter between those two places. But even then, right, there's lots of gas and dust like in the solar system and stuff. If you really want to find properly empty space where there's a very low chance of finding dark matter, you're going to have to leave the Milky Way. In fact, you're also going to have to leave what's called the local group, which is our collection of galaxies. You really want to leave even the bigger group of galaxies than that. You want to head off to one of these really, really empty patches of the universe. We see some of them in the cosmic microwave background, these places where there's a lot less of everything than there is elsewhere.
So there's a question: how has the spring model that you talked about been demonstrated in the last 100 years?
Well, this is a much more recent set of measurements. Actually, it is only within the last 100 years. It really starts with this man named Oort. If you're familiar with the edge of the solar system, there's something named after him, the Oort cloud. He came up with these things called the Oort constants, right? And these are measurements of the motions of things. And people noticed that the values didn't quite line up with what they should. In fact, my advisor, Joe Bovey, wrote an influential paper on this. So that's as recent as, I think, 2012. And it's still a very active topic of investigation, right? Because no star really lives long enough to go up and out and down and back, to really go through multiple oscillations. What you have to look at is the behavior of thousands, if not millions of stars to really suss this out in detail. And this is where modern technologies like the Gaia telescope, which is one of the resources I use for my research, come in. These fantastic telescopes that sit out way in space at what's something called a Lagrange point, which is a very stable point in space, so they can go and measure the positions of over 2 billion stars in our Milky Way. And also, not only do they measure their positions, but they also measure their it's called proper motions, which is their motion, their velocity. So this is as recent as last year that we got more data from Gaia, and these things that help us improve and make these more detailed measurements. So cutting edge stuff. Okay, part 3, taking the case further afield, right? We had the disk of the Milky Way, which is our sort of solar neighborhood, the place where we live. Now we're going to move a little further out to the stellar halo, and then even beyond that. The stellar halo is actually the largest in volume, but the smallest in mass part of our Milky Way. It is this diffuse cloud of stars, and unlike the bulge or the disk, where the stars orbit in these nice regular patterns, recall in the disk, they kind of orbit in circles, like our Earth around the sun. In the stellar halo, they're orbiting every which way. They've been set on these random paths, ellipses going this way, going that way. It's very, very random. Some are moving fast and others slow. And it turns out that there is a speed limit, and we can see it in our Milky Way. There's a speed limit where if you're going faster than that, you're on the highway out of the Milky Way. And if you're going slower, well, you're going to stick around in town. That speed limit we see is around 550 kilometers per second. So let's take a look at why. If we're on Earth and you throw a ball really, really hard, well, what happens, well, for everyone who can throw a ball, it's going to go up and then come down. But if you could throw that ball at 11.2 kilometers per second, which is Mach 42, roughly, then instead of the ball going up and then coming down, it would actually just go up. It would escape Earth's gravity and never return, right? But Mach 32 is a lot faster than the speed of sound, so not even a professional pitcher can do that. If you're on the moon, the story is a lot easier. You don't need to throw at 11.2 kilometers per second. You actually only need to throw at 2.4 kilometers per second. Again, this is faster than any human can throw, but it turns out the US Navy actually has railguns that can propel projectiles using magnets at around this speed. So if we take a US battleship, and put it on the moon, for example, on the Sea of Tranquility, and had it point its gun straight up and fire a bullet, right, that bullet would never come down. And the point of all this is that this speed to escape the Earth or the Moon or Jupiter is called the escape velocity, and it depends on the mass. The heavier the object, the higher the escape velocity. That's why Jupiter, which is so much heavier than Earth, has an escape velocity of around 60.2 kilometers per second, while something which is much lighter than the Earth, like the Moon, has an escape velocity that's much lower, right? But this is us knowing the mass and then figuring out what the escape velocity is. Instead, what happens if we didn't know the mass and could look at all the things that are being fired and find the point where something just escapes? If we could do that, find the point of just escape, well, then we could actually figure out the mass of the thing we're standing on, right? So back in the day when people were, smart and used gravity with the Earth around the sun and stuff like all that, and or the Moon around the Earth, to calibrate all the masses of everything, right? If in fact they had just had the U.S. a U.S. Army railgun, on the Moon, they could have just figured out the mass right away. And the same is going to work with us in the stellar halo of the Milky Way. Right? Stars are moving in all directions. Some are fast, some are slow. But what we're looking for are the fastest stars, right? These fastest stars, the ones that haven't escaped or the ones that are just escaping, these are the ones at the escape velocity of the Milky Way, which means that they are going to tell us what the mass of the Milky Way is. So let's take a look. If we look at all the stars in the Milky Way and look at their speed, right? All these halo stars have a variety of speeds, different numbers of stars at low speeds versus at high speeds, but there's kind of a cutoff at 550 kilometers per second. We don't really see stars moving faster than that. And that's because the Milky Way is an old place, and the stars that were moving faster than this, well, they've had time to, take that on-ramp to the highway, and they've left the Milky Way and floating off in intergalactic space. And everything else, well, they stuck around in the Milky Way. So just like the Earth, Earth mass was 11.2 kilometers per second, and the Moon was 2.4 at the weight of the Moon, well, we scaled that up to 550 kilometers per second, and the Milky Way has to be around 1.3 times 10 to the 12 solar masses when you account for everything that's going on. And again, just like what we saw with the rotation curve and everything, this is telling us that there's around 10 times the mass of all the gas, dust, and stars that we see. We are missing 90% of the Milky Way's mass, right? We think that this escape velocity should be a lot lower than it is. But we're feeling all this mass, all this missing dark matter, right? This has set the speed limit to stay inside the galaxy. And so that's how looking at the stellar halo and looking at the speed of everything and then finding that speed limit can tell us that there's a lot of dark matter. Okay, so we're about to leave the Milky Way. We've worked our way from the disk out to the stellar halo, and now we're going to take a look at the Milky Way plus Andromeda. The Milky Way is the one galaxy sort of in the bright thing in the upper left, and in the lower right is Andromeda. And I said earlier that in part one, Hubble found that Andromeda is outside of the Milky Way. Well, now we're seeing it. Surrounding these two galaxies, these sort of are a whole bunch of smaller little mini galaxies, things like the Large Magellanic Clouds or the Triangulum. But really, Andromeda is our closest large galaxy, and it's going to be the only thing that matters in this thought experiment we're about to do, right? I call this the local group timing because when you put the Milky Way and Andromeda together with all these other things, what we're looking at is something we call the local group, which is the collection of galaxies that are orbiting each other, right, that really feel each other's gravity, that are connected together. This is actually the largest gravitationally consistent or bound structure. So when we let the universe continue evolving, eventually this is all that we're going to see. And even though there are all these little mini galaxies, if you look at the amount of mass, only Andromeda and the Milky Way are going to matter. So let's just ignore everything else. In 1959, Kahn and Wiltshire, these two clever folks, wrote down thought experiments. It's really almost a back of the envelope calculation for how to use the Milky Way and Andromeda to find out how much dark matter there is, how much missing matter there is between the two of them. And it goes something like this. First, we have the Big Bang, and all the material that forms Andromeda and also the Milky Way really starts at the same place. And the Big Bang is going to bring them all apart. When the Big Bang happens, it doesn't sort of make things rotate. It just forces things apart straight out. And so what happens with the things that form the Milky Way and Andromeda is, they're separated from each other without rotating around each other. They form the two galaxies and, give it some time, they start falling back into each other because of all the gravity between them. And because a collision between these two galaxies is going to cause them to merge, to mix up and actually form a different type of galaxy, well, we know that hasn't happened yet. So in this thought experiment, we can just assume that this is the first time the Milky Way and Andromeda are coming together. Currently, they're 750 kiloparsecs away from each other. That's much, much bigger than the Milky Way or Andromeda. They're moving at 125 kilometers per second, and they've had 13.7 billion years to go out and then start coming back in. Right? And if we run this back of the envelope calculation about how much mass the Milky Way and Andromeda has to have for the gravity of Andromeda and Milky Way to slow down that movement away from each other and then bring them back together, well, it turns out to be around 4 times 10 to the 12 solar masses. This is a really large number. But since Andromeda is around twice as massive as the Milky Way, right, we can ignore Andromeda for a second and realize that this is actually saying that the Milky Way is around 1.3 times 10 to the 12 solar masses. You may recognize this number. It's actually the same number we got for the escape velocity argument. And it's basically the same number we get for the rotation curve argument. Even this back of the envelope calculation agrees with all these other methods that what we see, this 1.3 times 10 to the 12 mass object, well, 90% of that mass is dark matter, and only 10% is normal matter. All that gas, dust, and stars is really only 10 to the 11 solar masses. That 10 to the 12, 10 times more is in the dark matter. Well, a cool thing about this thought experiment is it also tells us how much mass is in Andromeda, right? If the Milky Way is around 1.3 and we had 4 in total, then Andromeda is like, 3.6-ish, sorry, 2.6-ish, give or take a bit, times 10 to the 12 solar masses. So a super, super heavy object. And just like our Milky Way, when we count up all the stars, when we look at all the gas and all that dust and add it all together, it's not even close to 2.6 times 10 to the 12. It's only around 1/10 of that. So all that we've learned in the Milky Way, those same methods which we can apply to Andromeda, and even this thought experiment which works on the both of them, tells us something pretty universal about the universe. That dark matter is everywhere. It's not just in our galaxy, it's in Andromeda, which was the first galaxy which we realized wasn't in our own. And then as we've continued to look with more and more powerful instruments, like the Hubble Space Telescope all around us, we see that this same story is true of every galaxy. That's the dark matter, which is missing in the Milky Way, is missing everywhere. All right. So this was is an active investigation. And though I haven't discussed any of the suspects for the missing matter, right, we've heard some of that in the previous talk and in the next talk, right, we've seen so many of these facts of the case. We discovered the scene of the Milky Way really beginning in 1923 when we realized that we live in just one galaxy among billions. And then soon after, when we realized that there's so much missing mass, it's not just out there or in the early universe, it's also missing right here, right now. In looking around the Milky Way for the missing mass, we saw the rotation curve of the Milky Way, which told us that there's around 10 times as much dark matter as normal matter, And this dark matter isn't distributed. It's in the same positions as all the normal matter. It's spread out, even out to large distances. The vertical oscillations showed us all the dark matter in our neighborhood and in the neighborhoods all around the disk. The galactic speed limit gave us an idea of how fast a star could move and why all that dark matter in the Milky Way sets the speed limits, right? It would be able to move so much more slower before escaping, so there'd be so many fewer stars in the halo if we didn't have all that dark matter. And last but not least, we had a thought experiment about us in Andromeda, imagining us, being birthed at the Big Bang, flying out, and then coming back in because of gravity. And the amount of gravity that we need to do that, to match all our observations, is so much more than the gravity that we can account for with just the mass that we see. So the Milky Way, Andromeda, everywhere we look is full of dark matter. And all that we got from this first picture, right, of the Milky Way moving around, moving up and down, moving out, and then finally looking away. So, thank you.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.